My name is Lanxin Jiang from School of Mechanical Engineering at University. And my presentation today is the basic technology and image post-processing for fiber composites.
So you can use the mouse. Just the wheel.
My presentation has four parts. The application of micrositting in FRP, in situ test damage of FRP, the ex situ protective damage of FRP, and the conclusion. First thing, the commonly fiber plastic with the FRP engineering is the most carbon fiber reinforced plastic, CFRP, and the glass fiber, GFRP, and the carbon glass fiber hybrid laminates. And the matrix is usually the epoxy resin, widely used in aerospace rail transition. And the weaving type and the configuration types have the significantly affect the mechanical properties. So we can use the CT technology using on the FRP. There are two types of CT equipment. First is industrial CT or lab CT. And the second is in control radiation CT, just like in Shanghai light source. These two CT have different light source. Industrial CT have a lower brightness and lower resolution. Synchronous CT has extremely high brightness and higher resolution, but the cost is extremely high. These two CT, we can get many images and slices, and they have the similar post-processing procedures like the reconstruction and the defect analysis, 3D stream field analysis, and the light element model analysis. And the trend of the field, we can see during this year, the CT and FRP keyword papers is increasing, and the keyword is defect micro construction and porosity. And then we can see in this part, we can analyze the 3D visualization of pores and defects, and then by the technology of digital volume correlation called DVC, we can analyze the 3D stream field interlayer the FRP. So then the finite element simulation based on the CT images can establish to predict the parameters. In this part, I will introduce some research in our team. We conduct the in situ test of FRP. We use FRP, GFRP, and the carbon glass FRP. We call it hybrid FRP. In this in situ test, firstly we doing the static test, tensile test to get the ultimate load, and then we choose 4 to 5 CT scans point, so we can get these curves. You can see FRP have a straight line and the fracture is brittle. And the hybrid FRP and GFRP will fluctuations during the stretching process, At this step, this point, we take the scanning, the CT scanning. Then we get the slices. We can see in the hybrid FRP there are glass fiber, carbon fiber, and resin. And also we can get the carbon fiber, the model. Then we're doing the data processing flow based on a visual software and 3D reconstruction model and segmented the components. By the reconstruction model, we can see the fracture failure model. The FRP have a plane fracture, and the hybrid FRP we see the delamination failure. And in GFRP, we can observe many fiber float out. And during the in situ process, we can see the fiber. We can see in the layer, in the glass layer, the pore increases mostly, and during when the load increase, the fibers and the porosity increase. And then we can quantize every pores in the FRP, and the statistics of micro pores and medium pores and large pores. And we can see in the GFRP, different FRP have the different trends. Hybrid, then we can statistic the hybrid surface porosity, and the most largest pores is enter the layer, and these edge pores are easier to expansion. Then we're using the digital volume correlation by the pixel matching in 3D spaces. We can get the displacement distribution and the 3D strain field. This shows the 3D displacement field of carbon fiber layer and glass layers. And this is the 3D strain field of carbon layers and glass layers. We can see the carbon layers. The strain in glass layers is larger than carbon layers, and the strain field is not uniform, and we can predict the fracture position. And then we're doing some fatigue damage analysis using the CT technology. This is FRP and AL Baltic joint specimens. And we make two sequences and doing the fatigue test. At first, we also test the ultimate load, and then we get the SN curve, and then we scanning the FRP after the fatigue load around the hole. The resolution is 40 micrometer, and we can see after the fatigue load, there are zigzag failure, and we can also segment the carbon fiber matrix and pores. The S1 layers, 45 layers, we can see the pores gathering in the two areas, like the X shape, and the non-nutty layer. There are only one gathering area. So we establish a flat element model. We can see they have S1 and S2 have different stress distribution. So this is the reason we can observe the poor distribution. And then we also statistic the number of weaker poles and the medial poles. We can see the cycle number and the stress level will lead to an increasing of force and decrease the stiffness of the structure. And in this test, we doing some fatigue CT scans during the whole fatigue process with the hybrid specimens. We also doing the static test and get the S curve and the fatigue life and on the 0.9, 0.3, 0.6, and 0.9 for fatigue life. And we take the samples for CT scanning, and then we continue the loading. And in this part, we get the images, but the quality is not very good. And we found if we using the traditional segment method, we can't segment this parts. So we use the conventional neural network with deep lab v3 plus in Python. We manually calibrated over 100 defect images, and then we training the data and then automatically calibrated all CT images. After the training, and we can get the defect distribution after different cycle loads. And then we can predict the risk areas. Then we combining the SEM. We can see the 45 layer. It is undergo shear fatigue and with the matrix damage. In the 19 layer, it is the tensile fatigue. So almost the fiber crack. Then we can get the evolution of thick fatigue cracks in the whole fatigue process. Finally is the conclusion and the prospect. In the future, we want to change ex situ fatigue and change to the in situ fatigue CT test. And in the future, I think there are 3 key points. Firstly is rapid finite element modeling based on CT images, and the 2 is intelligent defect classification based on deep learning, and the 3rd part is structural strength assessment for the engineering applications. That's all. Thank you. And if you want to the discussions, you can add my WeChat or my email. That's all. Thank you.